So in this video, we're going to take a look at some ripple tank animations, and we're going to look at how we use the wavefront model in terms of modeling how a wave behaves as it's reflected, as it's refracted, and as it's diffracted. So let's first of all have a look at the wavefront model of reflection. So what we're going to do is we're going to send some plane waves, as they're called, up the screen, and then you can see they are reflected off the barrier, and then you can see them traveling to the left. So let's see that again. So they're going up the screen, they hit the barrier, and then they end up traveling to the left. So the wavefront has been reflected. Okay, so this is how we were used to seeing diagrams of reflection, using Newton's model of reflection, imagining that there are particles of light traveling along those rays, and we saw the angle of incidence equals the angle of reflection. Well, the wavefront model works very similarly, but instead of thinking of the particles of light, we're thinking of waves traveling through and being reflected off. So you've got the dark, thick blue line showing the incident wavefront, and the dashed lines showing the reflected wavefront. Okay, so that's what we would get if we were essentially reflecting wavefront off a plane barrier. So in terms of thinking about how the two models relate, if we put the rays onto this system, so the wavefronts, as Huygens imagines them, or Huygens as is commonly known, are always going to be perpendicular to the rays that Newton imagined. That's a useful way of relating the two models. Okay, so next we're going to take a look at refraction. So what we've got is a plastic block in here that's going to change the depth of the water. So let's send that through. Okay, so you can see the wavefront being bent as they travel over the shallower section. So let's have a look at that in terms of a wavefront diagram. Okay, so as the wavefront travels along, the wavefront doesn't change until it encounters the boundary. So you can see the wavefronts which have to travel further stay the same for longer, whereas the wavefronts where it hits the boundary first of all change direction earlier. And we can see the difference between when we have larger angles of incidence from left to right. And the reason we get this is that in water, waves travel slower in shallower water, often due to the drag at the bottom of the water. So this is our wavefront model of refraction. And again, I've put the ray diagrams on top of them, so you can see what's happening in terms of Newton's model of refraction as well. That's where the particles would be passing. Okay. So next we're going to take a look at a barrier designed to bend the rays or wavefront inwards. So let's see that too. So you can see that we're producing almost circular point type wavefronts when it focuses them in. Okay. So in terms of the two models, so the blue shows the ray diagram, or Newton's model of how a concave mirror works, and then the purple shows Huygens or Huygens, whatever you prefer, as model of it. So we can see we've got plane waves going in, as they're called, the straight line waves, and we can see that in the wavefront model they're bent into arcs or sections of a circle, concentrating at the same point. Okay, so now we're going to look at diffraction. So I'm going to show you diffraction with a few different size gaps. So first, with a gap about the same size as the wavelength of the incoming wave. So we can see that's what we get. And then we're going to increase the size of the gap. So what I'm noting here is the diffraction is less. So before it was much wider diffraction. And let's make it bigger even more. So we can look at it with a really big gap, and we can see the amount of diffraction gets even smaller. So the bigger the gap gets, the smaller the diffraction is going to get. And we can look at one more scenario that I didn't show you. What if the gap is smaller than the wavelength? And if you do that, the diffraction becomes smaller again that way. So if your gap is really big compared to the wavelength, you get basically no diffraction. As your gap gets smaller, we start to get some diffraction. We get maximum diffraction when the gap is the same size as the wavelength. And we have, as it gets smaller still, the diffraction then gets less. Okay, so now we're going to look at the interference of 2-point sources. So let's start that off. So we've just got 2 points producing waves, and then we've got them overlapping and superposing on one another. That's the word we use to describe 2 wavefronts meeting and their amplitudes combining. So what you'll notice is there are some brighter sections which are being shown up by the strobe, and those ones are where we've got a really big amplitude. So those bright spots where we've got a really big amplitude. And we've got the black spots where there's a really small or no real amplitude there. So we often refer to the bright spots as maxima and the dark spots as minima, or like 0 amplitude left over. So that's an interference pattern we've got there. So let's have a look at that in terms of the wavefront model. So a point source looks like this. It's just waves coming out in a circle. If we superpose 2 point sources on top of each other, we get an interference pattern. So what I'm going to do is I'm going to draw some lines to show where we make maxima. Is basically wherever you can see 2 wavefronts or 2 crests meeting. So they would be along these lines here, which I refer to as maximum lines or maxima lines. And in between those, we get regions where they cancel each other out, or a crest meets a trough, and that's what we'd call a minima point. And one thing to observe, if we move the point sources further apart, is the maxima lines, those lines I've drawn showing where all the maxima are, the angle between them gets smaller the further apart we move those 2 point sources. And that completes this video looking at wave fronts.